So let's wrap up activity 1.2.1. This was our introduction to the generators and relations viewpoint of group theory. And we were using, at the time, anagrams and, by extension, Braid-a-Grams as our algebraic object of study. And so the first things I asked you to do on that assignment, I'm going to dial back to it here right in our book, from Braid-a-Grams to Braids. So what I asked you to do was just do some calculations with a presentation of the permutation group called the Coccidr Presentation. Basically, it took each of the twists, each of the Braid-a-Gram adjacent transpositions, and it represented it by a generator that we called sigma I. So sigma 1 would trade the first strand with the second strand, sigma 2 would trade the second with the third, and so forth, all the way across our Braid-a-Gram diagram. And those are the generators, and we claimed that the relations were that, first of all, every one of those transpositions is its own inverse. If I do a 1-2 swap and then I do another 1-2 swap, the result is the same as if I hadn't done any swap at all. Right? So that gave us these order relations that the generators of the permutation group satisfy. We also had these relations, which told us that actually if I have two of those swaps and they're disjoint with one another, then those swaps are going to commute with one another. If I do one of them followed by the second, I get the same permutation as if I had done the other one followed by the other one. Because they're not competing over strands, they commute with one another. So that's the second relation that we have here. And then the third one are these so-called skein relations that says if I have two of my transpositions that do in fact share a strand with one another, if they overlap in one position, then doing one of them followed by the other one followed by the first one again is the same as if I had flipped that around and did the second one followed by the first one followed by the second one. Right? Those are called the skein relations. It's the most complex of the relations for the permutation group, and that's what we're capturing here. So you had the opportunity to kind of do some algebraic computations with those, sketch some Braid-a-Grams, and at the end of it, what I asked you to do is to try to soup that up just a little bit more. And in place of the Braid-a-Grams, so you built a Braid-a-Gram, right, that represented these different permutations. And then I asked you to do the same thing, but instead of just thinking of this sort of undifferentiated crossing as being the thing that I make my Braid-a-Grams out of, I then asked us to consider what happens if we want one of those strands to be an overstrand and the other one to be an understrand, the same way that we have it in diagrams for knots, which is ultimately where we're driving at with all of this, right? Is we want to be able to use these as tools to study knots, and so we're going to have to care in knot diagrams about overs versus unders. So what happens if we insist on caring about those things right now? So in Braid-a-Gram land, right, the permutation that turned et into t, which you wrote as sigma 2 followed by sigma 1, so reading this diagram from top to bottom, right, the swap of the second and third positions followed by the swap of the first and second, and the Braid-a-Gram, which resulted from doing 1-2, 1-2. In Braid-a-Gram land, those were the same permutation. We could directly show, both using the diagram and also using the algebraic rules for the generators and relations in the permutation groups, that those are actually the same permutation. But what happened when you made those braids instead of Braid-a-Grams? Are these actually the same braid, or do we end up with different braids? How did you all sort of think about that question? So when we talked about diagrams for knots, when we were first introduced to knots and diagrams a handful of weeks ago, we came up with these diagram rules, ways of knowing for a given diagram of a knot whether or not the crossings that I'm seeing in that diagram are really necessary, or whether we might be able to simplify and reduce my diagram to reduce the number of crossings, or to be able to somehow test whether one diagram and another diagram at the end of the day actually represent the same knot, because they're related together by diagram moves. Things that we decide don't actually change the underlying knot, they only change the diagram that we're using to represent that knot. And so I want us to be thinking about that same kind of question here. Is there a way that I can use those diagram rules to change one of these into the other? Here was the 3 diagram rules that they came up with when we talked about knot diagrams several weeks ago, right? And each one of them had the ability to either, in the case of the first rule, change the number of crossings in my diagram up and down by 1, right? Just by taking a loop and de-looping the loop, right? I can go up and down by 2 by taking an arc and crossing it over another arc, as we see here. And then the third rule was the more complicated one, right? It doesn't actually change the number of crossings, but it takes one crossing and a strand that passes under them both, and it just moves that strand from one side of that crossing to the other side. So these were the 3 diagram rules that we came up with. So with those in mind, I think what I want to do just to get us started today is ask you in your groups to take a look at these braids, right? The 2 braids that are turning eat into tea, which, as Amanda says, at the level of permutations, if we just look at the word at the beginning and the word at the end, right, the permutations are the same, which is why in Braid-a-Gram land, in the Braid-a-Gram algebra, we were able to use the algebraic rules for generators and relations of permutation groups to directly prove that these were the same permutation, right, because they're both turning eat into tea. And so the main question I want us thinking about today is when we make these positive braids, by making all those crossings over crossings as we go from northwest to southeast, can we tell, how can we tell whether or not these are the same braids, possibly using our diagram rules that we had from when we talked about knots and diagrams. And it may turn out that coloring these strands is a way to sort of keep them straight enough in your mind that you can sort of understand what impact the various diagram moves are having on what you're trying to accomplish. So Group B want to talk us through how you were thinking about whether or not you can tell that these 2 diagrams are equivalent or not. So what you're noticing when we try to make these 2 diagrams mesh somehow, right, to demonstrate that they are or are not in fact the same braid, I think all of your groups, as you were discussing, wound up queuing in on the second type of move, the poke-unpoke move. That seems to be the most natural way. If I have a diagram with 2 crossings and a diagram with 4 crossings, that poking move seems like the best way to try to find out whether or not they're related. Okay. And so your argument was, I'll come back to it here, that if we start with the diagram on the left and then just we take that blue strand and we sort of bend it around a little bit to try to create an extra pair of crossings with the red strand. This kind of looks like what you did there, right? Then we can do that just by moving the blue strand under the red strand in a poking maneuver, right? And so we go from 2 crossings to 4 crossings in doing so. But when we do that, what can we say about the orientations of those crossings? So in both cases, it looks like you have the red strand drawn over the blue strand. After all, that's part of this rule, right? We can't create any new intertwining. We just have to, both of the new crossings that we create by a poking maneuver have to be the same orientation. They either have to both be unders or they have to both be overs, right? When we do one of these type 2, 2-strand do-si-do is what I called them earlier in the semester. So what do we know about these 2 red-blue crossings as a result? So they'll bring us back to the original if we undo the poke, right? And so that's what makes this that's what makes the braid which is drawn here and the braid which is drawn over here on the left, I think we'll agree are the same braid, because all we've done is we've taken the blue strand and the red strand and we've just sort of bent the blue strand underneath the red strand, right? And so we know they're the same because they're related by one of these diagram moves, a type 2 move, right? But what is the orientations of those crossings? Here the red crossing passes over the blue, and so is that a positive or a negative braid generator? It's a positive, right? We decided that when northwest to southeast passes over the northeast to southwest, we call that a positive crossing. So I would label this a positive crossing. But what kind of crossing am I going to get here when red goes back over blue? That one's going to be a negative crossing. It's behind my big head right here, right? But when the northeast to southwest passes over the northwest to southeast, we call that a negatively oriented crossing. And so I guess what I would invite us to think about is when we do one of these type 2 moves to a braid, what kinds of generators are we going to be adding into my braid? Or what do we know about the signs of those generators, positives and negatives? What can we say about those, if anything? So ultimately, because this type 2 move does not change the essential braidiness of a braid, right? We expect that in the algebra, this type 2 move is going to be invisible. It's going to cancel itself out in some fashion, right? And the only way, it seems, to make that work, right, is to appreciate that one of the crossings that we create, one of the extra generators that's going to get thrown into my braid word as a result of this poking maneuver, one of them is going to have the positive orientation, and the other one is going to have the negative orientation, right? So that at the end of the day, the 2 are just going to cancel one another out. they're going to wash. It's like adding one and then subtracting one. Right? It's one of those classic, we're working in an algebraic expression trying not to change its value. So whatever we do, we also have to undo. It's like when you're completing the square, right, inside of the parentheses. Oh, we have to add 8 here to make a perfect square, but we also have to subtract 8 again so that we don't change the value. Same kind of thing is happening here. When we poke a braid, right, by passing one of its strands underneath the other one, we create 2 new crossings, but one of those crossings is going to have the positive orientation, and the other one of those crossings is going to have the negative orientation. So why is that a problem for this pair of braids? What kind of crossings does my more complicated E to T diagram have? It has all positive ones. That's how we created that braid in the first place. We said, if all of our crossings have the positive orientation, let's build this braid and see what happens. Right? But there is no way for us to turn this simpler diagram into the more complicated diagram, go from 2 crossings to 4 crossings, using my diagram moves, right? Using these moves. There's no way for me to change the one into the other, because to do so, I would have to generate new crossings that come in positive negative pairs. Right? And we can't possibly do that when all of the crossings that are in my more complicated diagram are positive. So there does seem to be a fundamental irreducibility here. Right? There's not going to be a simple way, in fact not any way, for us to reduce this 4-crossing diagram of a braid into this 2-crossing diagram of a braid without using something which is not one of my equivalency moves, my Reidemeister moves. Right? So I think that is enough of a proof for us, right, that these 2 braids are in fact distinct. Right? These are not the same braid, even though the braid-a-grams, the anagram that turns E into T, right, the permutation that is induced by the strands of the braid is the fancy way that we would say it. That permutation that's induced by these 2 braids is the same. They both turn E into T. But when my crossings all have the positive orientation, as they do here, we actually get a different braid connecting E to T in the latter case versus the former case. And so I want to return back to the argument that we made when we first were working with Braid-a-Gram algebra, when we were showing that the 2 Braid-a-Grams were indeed the same. The argument that we made there was a purely algebraic one, right? We took sigma 1, sigma 2, sigma 1, sigma 2, the 4-crossing Braid-a-Gram, and we used the relations, and the relations we can find here from the Coccidr presentation, right? We used the relations in order to show algebraically that those 2 permutations were actually the same. We did that, you did that, by first using the associative property to group 3 of these letters together, and then use a skein relation. So that's the third one of these equations, the third one of these relations right here. You use that to turn 2, 1, 2 into 1, 2, 1 instead. And then after another associative property regrouping, we got a 1 and a 1 together. And then when a 1 and a 1 was together, we could use this first one of the relations, the order relation, to just replace sigma 1 with identity, right? And so there, algebraically, is how we proved that the 2 Braid-a-Grams were in fact the same permutation. So then the question that I want to pose to us now, this is the big question after which we'll take a few minutes of a break before we come back, is what do you think goes wrong? Which one of the steps that we did in this algebraic simplification no longer works when my Braid-a-Grams are replaced by actual braids with all positive crossings? So what's the weak link here? Which one of these pieces of argument do we think doesn't work anymore? If we're worried about the associative property, then what we could do, for example, is build sigma 1, sigma 2. So that's crossing the first pair of strands followed by the second pair of strands. And then after that, follow that up with a sigma 1. So we would have this happening. So that would be the braid that I get by doing sigma 1, sigma 2 first, and then following it by sigma 1. And when I do my braids, by the way, I read from top to bottom. Not every author and every textbook uses the same convention, but that's just the one that I prefer. Versus the braid that I would get if I did sigma 1 first, and then after that, did sigma 2, sigma 1. So sigma 2 is this one over here, and sigma 1 would be this one over here. So there are my 2 braids, and I guess I'm just asking, are these 2 braids the same braid? And I would say, yeah, it looks like we can just kind of all I've really done is I've just kind of taken this twist over here and I've just kind of moved it vertically a little bit, just sort of nudged it up and down, right? Which that's not even one of our diagram moves, not one of our Reidemeister moves. That's just a planar isotopy. All I'm doing is I'm moving the strands inside of a three-dimensional space without changing any of their orientations one with another. So I don't think we're going to be able to indict the associative property, thankfully. And that's really thankful because it means we're still going to be able to consider braids as forming a group. If we lose the associative property, we completely blow up our ability to use group theory. We can use maybe different kinds of algebraic theory, but not group theory. So associativity is okay. What else might we have lost here? The skein relation seems like another obvious target, right? Because it's kind of a complicated relation, right? And so maybe there's something that's special about the skein relations when it relates to permutations that's different when now we're looking at braids instead. So to investigate that, let's look at the same kind of picture again. But instead of trying to vary my groupings, I'm going to try to just draw in my skein relation. So sigma 1, sigma 2, sigma 1 is one of my braids. Nudge that over here. And the other braid that I want to study is the opposite, sigma 2, sigma 1, sigma 2. And I want to figure out whether those are the same braid or whether they're different. All right, so 1, 2, 1. I'm going to do a crossing of the first pair of strands, followed by the second pair of strands, followed by the first pair of strands again. By the way, we're going to have technology today draw braids for us a little bit later on. It's a lot better than my clumsy finger on an iPad. But so there's the braid 1, 2, 1. And then if I draw 2, 1, 2, I'm going to cross over here first, then I'm going to cross over here, and then I'm going to cross over there one more time. Connect those up. So here are my two braids. And so I just am trying to convince myself whether or not we have the same braid in these two pictures. And so what we might do, if we believe that the skein relation is still satisfied, then the only possible step of this process that could fail is where? The final step of the process, right, is where we took sigma 1, which is two consecutive transpositions, right? You swap the first and second positions, then you swap them again, and replace them with an identity. It cancels itself out, right? And the reason for that in the world of Braid-a-Grams, if I go back to my diagram here for a minute, right? If I have a Braid-a-Gram and I do something like this, right? So this would be sigma 1 followed by sigma 1 in Braid-a-Gram world, right? Then because there's no orientations to these crossings at all, right? We're only paying attention to the permutation that's induced. Right? So this would be like turning the word no into the word on. Or, well, doing something to the word no, but then if I trace these through, the N that started in the first position ends up in the first position. The O that started in the second position still ends up in the second position. And so at the end of the day, this Braid-a-Gram is the same Braid-a-Gram as if we had done no transpositions at all, right? And so sigma 1 is equal to the identity. Right? But then what happens if I do two positive twists in a row in a braid? I get something that looks like this. And we can show, again, using that same diagram moves argument that we used in the beginning of class, we can show that there actually is no way to transform this doubly twisted braid that I have here into this completely untwisted braid over there at the right. Because in order to do so, we would have to have, if we started with this braid over here on the right, any crossings that we introduced to make it more complicated would have to be added in pairs of positives and negatives, right? And that hasn't happened here because I have two positives that are a part of my braid. And so in braid world, our generators do not have order 2, right? My generators do not undo themselves. If I do a twist where the orientation of that twist actually matters, and then I do another one of those same twists, I'm not making my twisting any simpler, I'm just making it more twisted, right? And so however many times I want to do that twist, I'm going to keep creating new twists in my braid. It's just like when we talked about rational tangles. and the rational tangle generator T, where if I do T a whole bunch of times on a rational tangle, all I'm getting is more and more and more twisted. In rational tangle world, we had a way to undo a twist because we also had a way to rotate the whole rational tangle, that if we rotated and twisted in the right combination, we could actually untwist a twist. But in braid world, because we can't rotate anything, once we make a twist, it looks like we're pretty much stuck with it, right? We can't untwist it just by twisting more and more in the same orientation. Instead, what would I have to do in order to undo one of my positively oriented twists? What's the quickest way to undo a positively oriented twist? No, just add a negatively oriented twist. We call that the inverse, sigma 1 inverse. And now, what rule is it that guarantees for me that this braid is in fact identical to this braid? What diagram rule am I using there? So what we notice is that that second diagram move, the poke, right, is actually responsible for convincing me and us that this diagram and that diagram are actually the same, right? These braids are the same. Sigma 1 followed by sigma 1 inverse. That's why we get away with calling it sigma 1 inverse, right? Because it undoes that sigma 1 twist, right? Because of that second diagram move. I can just pull this strand back across that strand and just straighten them out. And one thing that we notice, and is kind of leading us to a possible conjecture here, right, is that if we count the number of positive crossings and the number of negative crossings in a braid, that number, that braid sum, seems like a good candidate for a braid invariant, right? A quantity which depends only on the underlying braid itself and not on the particular word that we're using to represent that braid. And so here we would sort of say, here I have a positive crossing, which will count as a +1. And here I have a negative crossing, which would count as a -1. So if I add those together, I'm going to get this braid sum of 0 for my braid over here on the left. Right? Whereas my braid over here on the right has no crossings at all, and so it would have a braid sum of 0 as well. And so if we wanted to get conjectural about this, we might say, conjecture, if I have two words that represent the same braid, so I'll call them W1 and W2. If W1 and W2 represent the same braid, then the conjecture is that the braid sum, I don't know what I'm going to call that, sigma of W1 is equal to sigma of W2. Sorry, that's spilling off the bottom of my screen a little bit there. That's what I get for not having my Apple Pencil today. But if that conjecture is actually a true theorem, if that's a true fact, then that gives us a really powerful way to look at two braids and at least have a screening criterion. If we compute their braid sum and get two different values, that's the contrapositive of this statement. If the braid sums are different, then the original words must have been different, right? So if this is actually true, we can use it as a screening criterion. We can tell for sure when two braids are different if their braid sums of their diagrams happen to be different. It doesn't tell me that if the braid sums are the same, then the braids are the same. But we do know, if this conjecture is true, that the contrapositive would tell us that different braid sums give me different braids for sure. And again, if that were the case, we could have immediately looked at these two braids and said, well, all of my braids here are built out of positive crossings. So my braid sum for this first diagram, which contains 2 positive crossings and no negative crossings, that would have a braid sum of 2. And my second diagram, because it has 4 positive crossings and no negative crossings, would have a braid sum of 4. Right? And so we could say, if this conjecture were true, then for sure having 2 different braid sums means that we have 2 different braids.